Okay, welcome back. So we were just looking at this phase diagram. So again, let me summarize one thing. So let me use the blue again. Okay. So we took the derivative of x2 dot with respect to x2 because this is my chosen direction now. Okay, it doesn't have to be that, but look at this. X2 dot is a function of x2 only. All right. For this reason, I just took the derivative with respect to x2. Now this derivative is always negative, right? Because this is a square term, and then there's -3 here, so this is always negative. For this reason, if x2 increases, x2 dot constantly decrease, right? So if this is 0, this blue line represents x2 dot being equal to 0, then I have plus here and minus here. So what does it mean? In this region and in this region, okay, and in it increases. In these regions, it decreases, right? Remember, we have 5 regions. 1, 2, 3, 4, 5. Right? Now, we're going to do something similar for x1. Okay? We're going to do something similar for x1. So I'm going to look at the derivative of x1 dot t with respect to which variable is easier? x2, right? x2 is easier. So what is that derivative? The derivative is equal to 1, which is always positive. So again, in this direction, right, x2 is increasing. What happens to x1? Well, it is first positive,
Negative.
then 0, then negative. So first it is positive. So below the green line, it is positive, right? Above the green line, it is negative. So below the green line, I have only one region, right? Here. And both below blue and below green, I have an increase in x1. Okay. Then here also, I have an increase, and here I have an increase, right? Now, above the green line, x1 will decrease. Okay? That's it. So, if I draw another version here for clarifying the regions, we have that. We have that, right? So I have this dynamic here, this dynamic here, this, and finally I have that. And of course, in this region, I also have this, right? Because these are the same. So what do I see? Remember, I have 2 steady states, and I'm interested in the stability of these 2 steady states, right? Now, which one is stable?
Left one.
The left one, right? This one. Because here, the system moves towards this steady state. What happens here? Here, we have something like this actually, right? So this is stable, I understand that. How about this? Can I be certain about stability or instability of this? Now imagine the movement. If I am on that line, x1 dot equals 0, if something keeps me on the line, I move along the line, right? I move along the curve. But I cannot specifically say whether this is what we otherwise call a saddle path. So I'm going to now introduce you some equilibrium types. Okay. But the idea is that if you are not, if you are working with a nonlinear model, and if you are doing only a graphical analysis, then sometimes you cannot be exactly sure. Okay? Why? Because in a nonlinear system, here we understand the behavior of the system in a global way, right? For the entirety of this region, for instance, the system moves like this, right? For the entirety of this system, the system moves like that. So in that regard, this is a global type of understanding. I'm covering the streamlines for the entire regions. If I do linearize the model, I'm going to do that linearization around the steady state. For this reason, my analysis will be true only around the steady states. Okay? Only around the steady states it will be true. But it will be concise, it will be accurate. All right? In this neighborhood, it will be accurate. Because the linearized system would look like that. Okay? In the linearized system, I will have two linear equations. So I can solve them. I can be exactly sure about the dynamics in the neighborhood of the steady states. Okay? That is the trade-off. If you linearize the model, you study locally, but much more accurately. If you do not linearize the model, you see the global behavior, but sometimes for some type of equilibria, you cannot tell whether it is stable or not, because you have to check the eigenvalues, okay, to be exactly sure. So do you have any questions about this? Now, in a moment, it will be much more clear. It will be much clearer in a moment, because I will show you the types. I will show you the types of equilibria. But the trick is that if you do not linearize the model, you basically look like derivatives like this, okay? And you infer the sign. Once you infer the sign, you're going to understand the direction of arrows, the laws of motion of the system out of steady states. Then you can tell me some stuff. You can show me some stuff. Otherwise, as I will show you next week, you're going to linearize the model. Once you linearize the model, you're going to be much more accurate about the dynamics, but only in a neighborhood of the steady state. Here, I only know this is true. Here, I will be exactly sure how the system behaves. okay, around the steady state. That's it. Now, if you do not have any questions, I will show you the types of equilibria. Okay. If you have something like this, this is called stable node. Okay. Otherwise, you may have something like this. And of course, this is called unstable node, right? You may have something like this. In one direction, it is converging to the steady state. In the other direction, it is diverging from it, and this is called saddle point or saddle path. Okay. You have something like this. Okay, or you have something like this. Now these are spirals. Okay, now this is a stable spiral, right? And this is an unstable spiral. Okay. You also have center. This is center. So stable spiral is sometimes called sink, and the unstable spiral is sometimes called source. Okay, so these are the most commonly encountered types of equilibria. And again, once we linearize the models, then we're gonna see which one is node, which one is spiral, which one is center, which one is saddle path. Okay, because the eigenvalues of the linearized systems will tell us exactly which one is true. Okay. So any questions about this? Hello? Again, this material is directly from your textbook.
Mikrofonunuz kapalı hocam.
Hocam sesiniz gelmiyor.
Okay, something happened with my internet connection, but it still records.
Yes.
Maybe later on, starting next week, I can give some of you the permission to be co-host. For instance, Oğuzhan, so he can also keep recording. This is strange, but today I have classes for the entire day. Maybe the connection gives some warnings. So I was just, so when did I interrupt? I mean, when did I get offline? I don't know.
after the finalize the sketches.
Okay, all right. So you see it now?
Yes.
So I was just saying, so these are straight from your textbook. You can check the concepts from there as well. And once we linearize models starting next week, you're gonna see exactly how we know which type is which type. Okay. The idea is that when I have the system like this, okay, this is a nonlinear system, so this will be transformed into a system like this. Okay, where A is an n by n matrix. Okay, so then this matrix will have eigenvalues. And of course, eigenvectors associated with them as well. But we're going to look at the values. We're going to look at these values, and they will be lambda 1, lambda 2, dot, 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 lambda n. These values, of course, will depend on the parameters of A. These parameters of A will depend on the derivatives of f. Okay. Whether or not these eigenvalues are real, whether or not these are positive or negative, will tell me exactly which one is the case. Okay, will tell me exactly which one is the case. So let's make another example. Let's take another example. So how do I open a new one? Okay. So let's measure another model. Suppose that wealth is accumulated in this way. So I have RWT minus CT, okay? And let's say consumption is accumulated in this way. So it is alpha minus, let's say, WT. Okay, so here R is greater than 0 and alpha is greater than 0. Okay, now is this a linear or a nonlinear system?
It's a linear system.
No, it is a nonlinear system. The first equation is linear, but the second equation is nonlinear, right?
Okay.
Because it's alpha CT, CTWT. Okay? Now, how many steady states we have? So I need our W star equals C star and C star times alpha minus W star equals 0. Right? Right?
Yes.
So how many steady states do I have? So number of elements in S. Think about it. It's not that hard. Okay, we have two steady states, right? One steady state is C star equals 0 and W star equals 0. The other is C star equals R alpha and W star equals alpha, right? Look at these 2 points. So C1 W1 star, C2 W2 star, two steady states, right? If you put this into equations, they satisfy the equations that define this steady state. Okay. Now the system was again W dot equals RW minus C, C dot equals C times alpha minus W. So let's draw them. So let's say this is W, this is C. Okay, what do I have? Now, first let's look at C dot equals 0. How can we define this set? Well, if you look at this carefully, I need what? If C is equal to 0 and W is any real number, then this implies C dot equals 0. Or if W is equal to alpha and C is some real number, again, C dot is equal to 0. Right? So either I have this, so let me use red one and let me increase the size. So if W is equal to alpha, okay, and C is any real number, this is C dot, or C is 0 and W is any number. Okay, this is 0. So the red thing is C dot equals 0. Okay. Next, W dot. So W dot is equal to 0 only if C is equal to RW, right? R is positive. So I have what? I have this. Right? So I have two steady states. One steady state is here. And another steady state is here. Now, how do we understand the system's behavior? So how many regions we have? Well, basically, we have 4 regions, right? This, 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 and this, because we don't have negative consumption and negative wealth. Well, let's say this model is a simple one people cannot borrow. All right. So in these 4 regions, I want to understand the behavior of the system. So what do I do? Well, I'm going to look at derivatives, right? So let's look at the derivative of W dot with respect to C, which is equal to -1, always less than 0. So if C is increasing, it is decreasing, right? So in this direction, on this direction, it is positive, 0, negative. Okay, so W is increasing below the line and decreasing above the line. Okay. Then I have derivative of C dot, let's say with respect to W, okay, which is equal to minus C. Now I'm interested in positive values of C, then this is always negative. So this is now my direction, right? This is my direction. W is increasing. And when W increases, C dot decreases. So it is positive, 0, and negative, right? So it is positive, 0, and negative. So on the left of the C dot curve, C increases. On the right hand side of the C dot curve, C decreases. Now, what type of an equilibrium is this? It looks like,
Saddle point.
this looks like a saddle,
Yes.
right? Converging in this direction and diverging in this direction. Okay. Now, any questions? Okay. So just to give you some idea about what's going to come next after this topic, I mean, not next week, after when we start dealing with continuous time dynamical systems. For instance, we want to understand how the consumer would determine this. I mean, this is basically budget constraint, right? So there's not much discussion about this. But how does the consumer know how to increase consumption? Now that will be requiring dynamic optimization. Okay? So the consumer will choose a path of consumption and wealth to maximize some objective function. Okay? Okay. So we have about 3 minutes. We can use this time for questions and answers. Sorry, if I leave something unclear,
No.
let me know. Yalçın raises hand. I mean Yalçıner.
Yes. Can I ask one question? To be sure, if the points is not stable, we cannot linearize the model in that direction, or?
No, I haven't said that.
Okay.
What I am saying is this. First, if you have multiple steady states, you can only talk about local stability. Second, we have two options. Either we're going to go with the nonlinear model and draw the phase diagram. By drawing phase diagram, we're going to know exactly how the system behaves in any region. Okay? We're going to find these arrows. But sometimes that is not enough to distinguish between different types of equilibria. Most of the time, we're going to understand that, oh, okay, this is stable node, or okay, this is saddle pad, etc. But sometimes we cannot distinguish. For instance, if it's a spiral, okay, if it's a spiral, you cannot distinguish whether it is stable or not. Okay? For that, you have to linearize the model and check the eigenvalues. Okay? Then you understand whether it is stable spiral or unstable spiral. But there is a problem with this. There is a cost. The cost is that now your analysis is true only around the steady state. Okay? Your analysis is true only if you are close enough to the steady state. Why? Because you linearize the model. You're going to see this next week. So once we linearize the model, I can exactly tell you what type of equilibrium is that, but that analysis will be true only if I am sufficiently close to the steady state. Okay, so there is that trade-off. We have less than a minute. Would you require to log in again, or we're going to say goodbye?
Thank you.
All
We
right,
can goodbye.
all right, I think there's nothing more. So I will see you next week. I'm going to upload this stuff to the web so you can check back. And next week, we're going to look at linearization.
Okay, thank you.
All right. Bye-bye then.
Thank you.
Thank you.
See you.
Bye-bye.